got some solutions submitted to me for our latest homework. So
Mine's
let's
pretty
start taking.
juicy, not gonna lie.
Mine's also pretty juicy. So here is Edgar's solution. Let's take a look. Oh, all right. I like this right off the bat. So the first question was for 1.1 to do a power function that takes in a float and an exponent for that float, which is an integer, and then computes what the power of x to the n is, essentially. So let's take a look. We got a double answer here. Well, this is going to be slightly problematic in the event that the double is going to be downcast to a float because doubles are much wider than floats. So this would be perfect if this was a float, I assume. The issue being that you have to do a downcast from a 64-bit double, which has more precision, to a 32-bit float, which that's going to cause a few issues, but not anything major. All right, so then for the loop, I plus plus. Oh, this is interesting here. So you're incrementing your loop. So you do a while loop here. Typically, you would do a for loop here since you know the amount of iterations that are going to go in advance. Typically, you use a for loop if you know the number of iterations the loop is supposed to do in advance, and a while loop in the event that you don't, or there's some weird magic thing that means that you don't have to means you have to use a while loop. So typically you would see a for loop here for at least best style, but this works as well. Okay, so while it's less than n, exactly, and you keep going until, so I is the counter, and while I, right, is less than the number of times you're exponentiating, you do x times itself that many times into the answer variable, which you start as x. Good. Okay. Let's see. Next thing, what are we looking for? Problem 1.1. So this was to. Oh, this is like your driver for it. Okay, this is good. Yeah, so you're actually scanning for input here. I see. This is very nice and fancy. And you have a driver that drives the power function. Okay, very nice. So my matrix, so the second question was to output a square of whatever character is input, an n by n square of whatever character was input. So as we can see, there is a matrix of a 4x4 matrix of A's here. Here's the driver. Takes in the character A and the number 4 and outputs this many A's. Very good. All right, let's see. Next up, sequential search or linear search, either or. Pretty straightforward. You should preferably declare your counter inside of your for loop as a. You would declare I just right here, unless you're using I outside of the loop, which you're not in this case. So this would be in I right here, and that's going to be standard practice, but it doesn't actually change anything. It still works fine, same way. Okay, let's see. So yes, you're basically checking if each element in the list is equivalent to X, and if it is, you return the index, and then if it gets through the entire thing and doesn't find it, you return -1. Exactly. Okay, so you wrote the recursive solution as well, which I didn't even get to. So this is if n is equivalent to 0. I should probably take a look at this. And you're using arbitrary. Oh, you're passing the size in separately. So on my assignment, I said to submit with a set size of just 10, or 5 for the linear search and 10 for the binary search. You actually go above and beyond here and are taking in a size parameter here as well. So effectively, this is pretty good. And you're doing that with the recursive solution as well. So you take in an arbitrary size array, which this is actually going to be a pointer behind the scenes, but we're not gonna worry about that right now because today is the pointer day, and we'll be talking all about pointers later on. Okay. So let's see, for the recursive solution, what are we doing here? So base case is if n is equivalent to 0. I'm assuming n is the size of the array. So this is if it reaches the end, then it returns -1. Otherwise, let's see, if the position right at the end is equivalent to x, you return n minus 1. Oh, okay, I see what's going on here. Right. So basically, you're making the array smaller by 1 each time, is what I'm seeing here. So, you're de-incrementing your index. You're passing the same array through each time. But the position you're looking at is getting decremented by 1 every single time until the end, in which case you're returning the fact that it wasn't found, which is -1. Okay, that's an interesting implementation. All right, going down here. Problem 2.1. Oh, this is your driver for 2.1. I see. Okay. So binary search here. This is the standard binary search implementation. I see where you have the index declared out here. Very good. I don't think I've seen it implemented with the L plus H minus L actually recently. This is very nice. Theoretically, it's faster to do the return statement at the end, since you're more than likely going to have this be the case that executes the most frequently. So it's better to check this first. But that's such a small time save in the grand scheme of things that it's not entirely worthwhile to complain about. Okay. Yeah, so this is just the standard binary search implementation. If anyone has any questions about binary search, I don't want to waste too much time going over what binary search is, but if anyone actually wants to understand what binary search does, by all means, contact me here. Let's see. So going down, yeah, and you're getting literally the size of using the size of operator. Very good. Let's see. I'm assuming this is what, your driver right here, or is this? Oh, this is the recursive binary search. Very good. All right. We won't cover that one, but I'm very happy that someone implemented the recursive binary search solution. I will take a more in-depth look at that later, and I'm pretty sure it's probably right. Found recursive, yeah, 8 right here. So I'm sure you've tested that, and that is very good that this was implemented. All right, there's the driver. Yep, fine. Recursive. All right, so you've implemented this as basically checking if the number is prime. Okay, so if n is 2 or 3, then you say it's prime. Then you check if it's 1, 0? Oh, yeah, right. So 1 isn't prime, 0 isn't prime. Anything divisible by 2 isn't prime. Anything divisible by 3 isn't prime, right? And then you have a separate algorithm here for checking. Okay, so you're doing right. So this is a trick that mathematicians use. You only have to check up to the square of the number to see if it's actually prime. This is actually a very clever trick, but unless you know the fact that you can only have to check up to the square of the number to check if it's prime, people don't typically implement it this way, but this is good. This is like the super fast secret math way to implement it. All right. Then down here you have your, I assume this is like your driver here. So primes found, 2, 3, 5. Yes. Very good. I actually don't think, I was lazy and didn't even bother doing, I just had mine say that 1 and 0 and 1 were prime, which obviously is false. But I am too lazy to actually go through and write the big is prime function. All you have to do, though, is implement a thing that says, no, you're not prime if it's 0 and 1. Very good. So, yep, this is all good. Now we're going to go roast Dan Yee's code. Let's go roast Dan Yee's code. Dan, where's your code?
Discord DMs as always.
All right. Did anyone else send me a file? I don't think so. I think Max is still doing homework 1. All right.
I need some stuff now. Most of everything's done but the binary search.
Nice.
Can we send ours in for review, like, after our little break that we have?
I don't know what you mean by that, but yes, sure.
Like,
send it in whenever.
New Year's break, like little no session break. You know what I'm talking about?
Oh, yeah. All right. Exponential iteration, good. Let's see, just off the top of my head, you have this product here, which equals Oh, you set yours equal to 1 initially. You're missing out on, you're doing an extra cycle here, Dan. You can save a cycle by having this equal to the base and then doing one less cycle in your for loop. Let's see. Exponential recursive, very good. Right, so you take the base, the power. Wait. Oh, you implemented this recursively as well. I didn't even ask for this. This is great. Good work. All right, n by n square, pretty straightforward. The double for loop with this on the new line, very good.
I didn't do the n by n recursively. I did try though, and then I realized it wasn't working, so I gave up.
You could feasibly implement anything that you can implement iteratively can be implemented recursively.
Yeah, but I was trying to like restrict myself to only having the 2 parameters, the character and the size, and I was just like I couldn't figure it out.
That's actually interesting. I don't know if you could do it with just 2. Well, obviously you can do everything with just 2 parameters if you have pointers, but in the event that you don't have pointers, you could do some bit twiddling magic. But let's not get ahead of ourselves. Okay. So down here, linear search is, what are we doing here? Construct a function that performs linear search. This is good. So you just go through each of the elements in the list. If it's equal, return I. If not, -1. Recursive implementation, basically the exact same thing that Edgar had. Very good. Binary search right here, the classic low, high, and midpoint here. Very good. Again, it's actually faster to check the other 2 conditions before the equality condition, since you're more likely to have these conditions happen first, but that's, again, not entirely worth criticizing. Binary search recursive right here. Very good. Very fancy. I'm happy you implemented the recursive. I didn't implement the recursive searches. I should have, but I was too lazy. All right. Infinity prime. Very good. Starting off with 2.
Read the comment after infinity plus 1. There's a comment far down the line if you scroll over to the right.
What is this? If you really want to wait IDK how many minutes, use this number. Okay. Pretty high IQ. Let's see. So you're saying that while the value is less than infinity plus 1, you're going to basically, so you do the double while loop here. So prime checker is less than value divided by 2. Right, okay. And then is prime false, break, prime checker plus plus. Okay. And then you find the next one, and if it's prime, this is very similar to the way that I implemented mine. And then you just have a tester here. All right, this is good. This is very similar to what I have. Here's my solutions to everything. It's pretty straightforward, basically exactly what everyone else had. I do a funky little for loop right here where I'm using the parameter as the for loop counter, which you can do because this is already declared and I don't feel like implementing another variable, but normally you would just have a separate counter here. That's fine. Here's my print square code, very similar to Dan Yee's and Edgar's code. I'm not doing anything fancy. I'm just here's a 3x3 square of asterisks. Let's see,
I have
linear
a question.
search. Yeah, go for it.
Why does C let you just use the same variable in 2 for loops at the same time?
What are you talking about?
Well, you have for int I and then for int I again.
I actually don't think that this is. Because it's yeah, technically this is illegal, but it's doing something. It's like doing variable shadowing. It was actually, I meant to put that this was J. This should actually be J. In hindsight, how did they let me do this?
Would that be undefined?
They're not even throwing an error. I meant to put J for this one and this one right here. This was supposed to be J's.
Would that be undefined behavior if it worked, or like? Considering it's not throwing an error, it's just working.
Well, let's. Oh, hang on. Well then,
you didn't change.
I guess I didn't mean that to be.
No, you changed.
I meant, okay, so maybe. Well, let's see how this actually interprets it as an assembly program. So if I go to compiler here, and we get rid of fringe. Okay, hang on. Let me just comment out this print prime numbers because this actually makes it take forever because it's trying to like compute it. So I'm going to go to not Intel ASM syntax because Intel is bad. We're going to go to our what was it? Print square. I want print square here. See how they're implementing our print square. So there is an inner for loop right here. Here's the outer for loop. So the outer for loop, I just want to know what it's circling. So the outer for loop is from here to here. My question is just, does it have a separate looping variable declared in the actual body? So this is at -4 RBP. This is at, yeah, okay. So the variable names, even though they conflict, it actually does have them declared as separate variables. So here's the first I, and then here's the second I. When we actually look at it in the assembly, it does count them as separate things, even though we're using the same name for them. So this, I'm going to say, is an example of, we'll call it shadowing, even though this is bad and you should never do this. I meant to use a different name here. It should have been J, and J. And this would have been the better way of doing it. All right. And it should compile to the exact same thing down here. So if we actually take a look at this, yeah, so same thing. Literally compiles to the same thing. It's just the different variable name here. But it doesn't really matter. But yes, don't do what I did there. Thank you. Good catch, Danny. Okay. Next up, linear search, very straightforward, same thing. Binary search, I do the same thing. I just call it left and right instead of high and low. And as you can see, I put my equality case at the end as the else case instead of the first case. All right. Then prime numbers right here. I do a for loop for them. This is an infinite for loop, which is bad practice. It should have been a while loop for this one. The inner one should be a for loop, though, for good practice, because you know how many iterations you need. Once again, you only actually, so there's multiple ways to actually speed this up. You can put a break here, which I believe Dan Yee had, where Dan had the is prime check, and then he did a break right here. Whereas another thing that Edgar did to speed this up is you actually don't have to check all the way for every single factor up to the number. You can check up to the square of the number. So if you want to actually get this down, you can, by hashtag include math.h, math.h, there we go. And we check to sqrt of num, and then I downcast this result. Oh, I don't even have to downcast it. They're so nice. Anyway, effectively, this is letting us run this way faster than we would otherwise because we're only checking up to the square root of the number rather than the number. This is a little trick that mathematicians have discovered for checking factors for prime numbers. Anyway,
James,
yes.
We did while loops because you said yesterday to do double while loop.
I said that you could do a double while loop.
No,
I
I'm pretty
didn't
sure.
say you.
No, yesterday you were just like, this will be a double while loop, so I was just like, okay.
Do we have that on the recording? Did I really say that?
Probably.
I could be wrong. Let's go watch the recording.
No, not now.
We'll find out who's lying.
Yeah, we're I want to know if I want to know if I was promoting bad practice yesterday, because I have to correct that right now if I actually said that. Effectively, I should have said this yesterday. You use a while loop when you don't know how many times. I might have even said this yesterday. You should use a while loop when you don't know how many iterations you're doing. You use a for loop when you do know how many iterations you're doing. But obviously, everyone breaks this style. Even I'm breaking this style right here because this is an infinite for loop, effectively. And yes, you can do that, but it's terrible style. This should have been a while loop, and the inner loop should be a for loop because you know how many iterations you're doing beforehand. That's the standard. But you can also use for loops in cases where you just want a nice way of doing incrementing, which is what I'm using a for loop here for. But companies would yell at you if you did this. They'd catch you in a code review and be like, no, this should be a while loop because you don't know how many times it's executed. Okay. So with that, let's see. Max sent me stuff. Are we going over Max's work? Let's take a look at Max's work really quick. Let's see. Is this Max, is this day 1 and 2? Or is this all day 1?
Day 1 and 2.
All right, we'll take a look at yours later. For right now, we're like half an hour in, so we should probably start the talk on pointers, which let me pull up the sheet that I have here. All right, pointers are the most exciting thing in the entire language, and everyone hates pointers. I love pointers. Pointers are great. You're going to love pointers too, I promise. They're a lot of fun. I don't know why I said pointers as handles to strings. Let's just do pointers as handles to... I wanted to cover strings next week, but I mean, I guess we can talk about them today. I did allocate like 2 hours for this, so it shouldn't be that big of an issue. All right, so why don't we actually talk about what pointers are? And to talk about what pointers are, I think it would be helpful to talk about what a program actually is first. So let's hang on. I'm gonna server mute Matt Keelian because even though your mic isn't open, I can hear things. Oh, I've been linked the video. Thank you, Danny. I will take a look at that after we talk about pointers. Time to pull up MS Paint so we can actually talk about what pointers are.
You should just get a tablet.
What does that mean? You mean like to draw?
Yes.
Nah, MS Paint is the best, okay? No one will tell me otherwise. I love MS Paint. Okay, so we've been talking about variables, right? So declaring variables is basically creating some box that you can put something in, right? But what we haven't really talked about is these boxes that we put variables in. When I say int I equals 0, we're creating this box that has 32 bits of information able to be stored in it. And this is a terrible version of 32 bits, but I don't even think that's fine. Give me 1, 2, that splits it in half. What I want is 1 here, 1 here on the end. We're storing 4 bytes in it, right? So we put 1 in the middle. No. Yes? What am I doing? Am I crazy? That splits into 2, splits into
1
3.
in the middle.
1 here. Is this 1, 2, 3, 4? I don't know what I'm on right now. I'm tired, and I for some reason I was like, that's 5 right before this. And I had no idea what was going on. Okay, so yes, when we declare an int, we're declaring a box that has a capacity for 32 bits of information, or in other words, 4 bytes of information. Now, the first thing that I'm going to do in this lesson is show what effectively, how we can measure what's actually in the box and how big the box is. So I'm going to duplicate this and create a new window, and we're going to look at how we can, why are we in the Zig programming language? This is not the C programming language. All right, so let's have int main, and we're not passing anything into main. Get out of here. We're going to return 0. All right, we are down to the lovely, most basic program in the world. Does not do anything other than return 0. Let me add a new execution only and move that over to the side. Okay. So program returns 0. So why don't we begin by creating a single box called I and put some data into that box. Let's put the number 32 into that box. Sure. So we have a box here named I, and inside of that box is the number 32. So to get the size of the box and to see how big this box actually is, we can use the size of operator. And you can see when I type the word size of, it turns blue because size of is considered a keyword, even though it's also sometimes considered an operator. Effectively, anything you put inside of the parentheses of size of, any variable name, it will tell you how big that variable is. So this tells you the size of the box that you have declared here. So when I declare int I, it is telling me that the size of I is 4 bytes. So that's 32 bits. If you want to know the bit number, you just multiply the size of by 8, and that's how many bits it is, because size of returns in bytes. So size of can be used to measure variable names, or it can be used to measure types. So I can type size of int here, and it also returns 4. I can type size of double, and it will tell me that doubles, which are 30, someone is saying something. The most basic program, it literally doesn't do anything. Thank you, Dawn. Yes, so anyway, doubles are 64-bit floating point numbers, so they have 8 bytes, and as we can see, they're 64-bit, because if we multiply the number of bytes by 8 to get the bits, they are 64 bits. I actually don't know if long doubles are a thing, or if those are also... Okay, so long doubles are 128 bits, or in our case, 16 bytes. But we don't talk about long doubles. Long doubles are illegal. Don't touch long doubles, kids. Just use doubles. And in C, just use floats, because floats are comfy. Okay. So the size of a float is 32 bits. The size of a short, we're expecting 2 bits. There's 2 bytes, 16 bits. The size of a char is 1 bit, or 1 byte. I don't know why I keep flipping bits and bytes. Size of a char, 1 byte. 8 bits, right? Okay. So
I have a question.
Yeah, go for it.
So kind of bringing this into like the kind of topic, like quick question about like storing these maybe like in an array, for example, like storing in a data structure. If I said like, okay, I want an array with like 4 characters, right? If I took the size of that array, would I get just a size of 4 bytes, or would there be any like extra space allocated just because it's an array of 4 bytes? Like, would it be exactly what you'd expect, just like 4 times the size of the chart?
Yes. So this is actually a good question. Let's demo this. Let's actually do this out. So if we have a character array C and declare it to be of 4 characters, what do you think we're going to get when we put our C in here? So we've declared an array that can store 4 bytes. What are we going to get when we do size of C? The answer may surprise you. The answer is 4. So it shouldn't actually surprise you that much. We've declared an array of 4 bytes. Each individual character is 1 byte, right? And then the size of this entire array is C. So size of C, 4. Straightforward? I think so. It's not that bad. So yes, if we have an int array on the other hand, though, so say we have an int array of 4 things here. So now we're declaring 4 boxes with the name I here. Effectively, each of these boxes is of size 4, and there's 4 boxes. So the total size of I is going to be 16. So theoretically, if you declare an array like this, you can use the size of operator to get the length of the array, but then you have to divide the length by the size of whatever the array type is. So if I do this by size of int, now we're able to get the length of the array here with this fancy expression. But I don't recommend getting the array size like this. I recommend storing the array size in a separate size variable and always using that. And that's how the C library likes you to work with sizes as well. It's not optimal at all to do things like this, especially when we start getting into dynamically allocated arrays with pointers. So we're talking about boxes right now, right? So effectively, when we declare an integer, it has this box somewhere. But the thing now that we have to think about is the fact that this box doesn't exist in the void. It's not just floating around inside of your computer. It's being stored in your computer's RAM somewhere. And RAM isn't the void. Things don't float around inside of your RAM. Your RAM is a large contiguous space of addresses. Just like every house in the United States has to have an address, every byte in RAM also has an address that is where that byte lives. So while we've been thinking about these boxes as just floating around in the void, they're not actually floating around in the void. They're lined up next to a bunch of other boxes, which are not in the void, but actually being stored inside of your RAM. So each of these individual bytes has an address. We'll call this one byte 1, this byte 1, byte 2, 3, 4, 5. But what's actually going on here is that these addresses are not starting at 1 for your program. We're going to say that they're starting at some arbitrary value x. So this integer is stored at x plus 1. This is stored at x plus 2, x plus 3, x plus 4, x plus 5. And effectively, it doesn't matter what our x value is. All that matters is that we actually know where this guy is living. And that's all a pointer is us taking where this guy is living and putting it into its own box. So effectively, all pointers are numbers that tell us where the variable lives in the contiguous range of memory. So let's actually take a look at this by printing out a pointer. So we're going to declare some variable I called int I, and we want to know where this guy lives, okay? So he lives somewhere at some address, and the way we figure out what address he lives at is using the ampersand prefix operator. So this operator right here, ampersand I, is the where does this guy live operator. So if I return, I'm not actually going to return it, I'm going to just print f it. So if I print f, I'm going to print it out as a D, but it actually shouldn't be printed out as a D, but I'm going to do it anyway. I'm actually going to do something very illegal here and cast this to an int. Don't actually do this. Oh, they do not like me. They are very mad.
No, you
They're
didn't
very
include
mad.
standard IO.
They're going to let me do it anyway, though.
Pound include
There you
standard
go.
IO.
Oh, I want this to be an unsigned int. Okay. Here we go. Hashtag include std io.h. Okay, so I'm going to print out our address as an unsigned integer. Are they going to yell at me that this is... Oh, they were yelling at me for not a return value there. Okay. So, all right, here we go. So what's going on here is we are currently printing out where I lives in memory. And you're seeing it's giving us this giant number right here, 3116094444956. So this is where our guy lives inside of memory. So we are basically saying, where does our guy named I live inside of this big continuous range of RAM? And we are taking where he lives by saying I ampersand, which gives us, again, keep in mind that this is a block of 4 values. When I ask where he lives, they give us the first value for the first byte at which is being stored in this big continuous chunk. But there's also all of these other bytes in here. So technically, if I took this address and then added literally 1 to it, I could get the next byte in here. But be very careful, because you cannot literally add 1 to this unless it's an integer to get whatever is in byte number 2. There's going to be... We're not going to go into that because that's horrendous, and you would never do this in a million years. But say for some reason you were storing different things in different parts of this int, this is not a good way to access it. Use your bit shifts instead, rather than trying to use the actual memory locations. Anyway, back to pointers. So we have where our boy I lives now. So we're printing out where he lives. And you might notice something funny. Every time I reload this program, it should give me that he lives in a different location. So if I take this away and have it recompile, you're going to see that that number should change each time. So if I do this, yeah, it completely changes. And the reason it's completely changing is because every time we edit it, it's going to put I into some different location in memory. But it doesn't matter that it's in a different location in memory each time we run the program. What's important is it's in one place when we run the program, and we know where that place is because we can ask it where it lives. So again, the first operator here, the ampersand operator, is the where do you live operator. So the question now is, what actually is this value? What is this value type? And how can we store where something lives? So now I can get where something lives. I can print out where something lives. But I want to be able to store where something lives. I want to be able to put this value into a box of its own. And the way that we put this value into a box of its own is with a pointer type. So I'm going to have int, and then star is the integer pointer type. So this means that we are looking at where an int lives, and whatever this variable name is, so I'm going to call this pointer to I. And now, whatever is stored, so effectively, we want to know where I lives, and I want to store the address of where I lives. So the way that I'm going to do this is say that pointer to I is equivalent to, I'm going to set it equal to where I live, literally the address of I. And here we have the pointer to I. So now I'm storing where a variable lives in another variable. And the type that we're using to do that is a pointer type. So int star means, hey, this is where an integer lives. Now, you're probably asking, why can't we store this as, someone's asking a question. Would it be better not to give I a memory location when it is actually initialized? If I declare 10,000 int variables, I feel like it would be better to just ignore them until I start using them. Can you rephrase this question, Matt? What are you asking here? I'm curious.
I was thinking like pretty much before, well, it was when you didn't have the pointer to I. You had int I, and then you were printing out I's memory location.
Yeah.
But I is not initialized yet, so I was thinking to myself, like, I guess that's kind of weird, the idea of, like, I guess it has to be marked somewhere, but the idea that it has a location in memory, even though it's not, it doesn't really represent anything yet. I mean, it's a variable.
So
but
this is interesting. So languages like Python, which literally declare their, okay, so this is actually a very core important point. So your box, when you declare a variable, your box is not literally created on the line that you, hang on, I'm all over the place. I want to be here. So when you declare int I is not created on this line. If I go declare int j all the way down here at the bottom of my program, int j is not actually being created down here. J actually exists the second main is called. And the reason for this is the compiler pre-allocates space for every variable declared inside of your program before it's ever run. So if I actually take a look at the assembly for this program, you're going to notice two things right away. So this line right here, where I'm allocating space for j and putting, let's put 0 in j right here. Let us go to, hang on. See, I want to change this to non-Intel ASM syntax. So I know we can't read assembly. No one here is trained to read assembly. Let's take a look at what's actually being declared in here. Let me get rid of all of this pointer jazz right here. But effectively, what's going on here, I'm going to set j equal to 0 and I equal to 0. Something very fun is going on here. Effectively, are they not going to be... Why are they not actually allocating? Okay, I'm going to have to make this a separate function call. Give me a second. Because they should be subtracting from the stack, and they're not because it's main, and main is a special function. We don't talk about it, so I'm going to have f be a separate function over here. And we're going to have f do some fancy stuff, and then have main down here doing literally nothing. Let's see. Why are they not letting me... I return the result of f, even though f only gets 0. Why are they not doing the subtraction? They should be doing the subtraction on the stack for me, and they're not. I think it's because, is it because I'm not using these? But if I do j plus I, and like actually put something in here, they're going to do something then? 2, 5. I must be missing what's going on, because I'm not taking... For some reason, they're not subtracting off the stack, but they should be subtracting off the stack. What if I do it in Mips instead? I don't know if anyone knows how to read Mips, but they're doing some fancy optimizations here that I'm not actually able to work with. Let's go to Mips.
Subtracting off the stack, what do you mean by that exactly?
Okay, so effectively, what I'm trying to show happen here is, let me actually get rid of all of this. If they actually let me do this, this will be a much better demo, but I'm having issues with them showing this on x86. Okay, this is exactly what I wanted to see. So this is Mips Assembly code, and we're not going to talk about Mips Assembly code in depth, but this will serve as a decent example for what we are trying to do here. So here they're going to be moving what? So they're literally moving 2 and 4 onto the stacks. That's what's going on here. Move 0, 2 into register 2. Yes. But then they're moving it into memory. Right. Okay. So effectively, long story short, these variables, even though they're being declared on separate lines and values are being assigned on separate lines, so J is being declared all the way down here, there's already been memory pre-allocated onto the stack pointer. So the stack has actually... I should probably talk about how a C program is structured, because now this is probably getting beyond the scope of what we're supposed to be discussing. I was planning on discussing this on Monday, but effectively, long story short, when you call the main function, every variable that can possibly take a value on in your main function has already been allocated in memory. And the way that we know it's being allocated in memory is the first line of main. So before any instructions from main even get compiled and anything executes, you can see right here that they're adding 24, or the stack rows down. So they're subtracting 24 from the stack register, which effectively means that there's going to be 24 bytes in main. And we can see that 2 of those bytes that are allocated are for the variables in I and J in here. So we're moving to some offset from the stack pointer here. They're using, I'm assuming they're using they're probably storing the return value in some of these bytes. But effectively, they've allocated 24 bytes of memory for main right here. And that's what's going on. But these have already been pre-allocated. I could do a ton of math right here and then allocate something else at the end and have another. So now if I declare int k down here, we're going to see that now they should be declaring, oh, they're literally not, because I'm not actually using it, and they're optimizing that out of existence. That might be why this didn't work before. But yeah, so now you can see that when I have another thing, they are now allocating even more bytes for this. And I feel like they're actually using... I wonder if ints are longs in Mips, because if they use 64-bit ints always, no matter what, because this is kind of strange that they would... I could have sworn they use 32-bit ints. I don't know why they're allocating so much extra space every time we add a new variable. So if I add a new variable
just be
here...
like a compiler-specific thing, or... I mean,
it's possible. I mean, let's see. So if I allocate some other variable f here, now they're not allocating any extra space here. They have 6, F, 32. They're probably doing some weird memory thing here that I'm not
this might just be like an
entirely
optimization
understanding.
technique.
It's so hard to understand what the assembly does half the time, because they optimize out what you want to show. And then, working with assembly, you have to have all your assembly demos like planned out beforehand, because you should never underestimate the compiler's ability to screw up pre-allocation of things. So it's...
No, yeah, I get it. I guess my question was just like, oh, you're declaring 10,000 variables. It's kind of weird to pre-allocate them, but I guess that's what the compiler did.
They are all pre-allocated, and that's why we have to do dynamic allocation, which we're going to be getting to today.
Yeah. Okay.
So we can see that all of these are pre-allocated to some degree. So in here, we can see that effectively what's going on. When this function is called, we have a register base pointer, and we're growing into the stack. I wonder if I actually call something from this function, if that's when it will do the allocation. Because once it calls into something else, I have it call itself. Which is... yeah, okay, so here we go. So that's why it wasn't doing anything, because it had optimized out for the fact that it wasn't calling it anything else. So it was always able to work with the lowest area in the stack, and it never actually had to like preserve what was inside of the stack. But if you make another function call from your function, in this case, I'm literally calling main. Please never do this. This is terrible. You can see now it's subtracting 16 bytes from the register stack pointer, our SP. And this is basically saying, so we've declared 4 ints. Each of these ints is 4 bytes. So it has to subtract 1 byte for each, 4 bytes for each int that's declared. So every time we declare a new variable in here, and we have this function call in here, so if I put this, now it subtracts 20 from the stack pointer. It's subtracting 32 from the stack pointer. There's some kind of optimization here that this is actually, what are they doing? So here's 20, and they're subtracting 32. I would have expected they would have subtracted 20, but apparently not. I'm apparently insane, and they're doing some kind of optimization here where they're actually allocating more than they have to. It made a lot more. Is this some kind of thing where they go up by powers of 2? I can't see this being anything else besides that, because they do 16 when you have 4. If it's 3, do they only allocate 8? No. So this would still be 16 when it's 3. Yeah, so they're going up by powers of 2, which is completely useless. I don't know why they would do that. It's probably some optimization thing that they're going for, where they increase by powers of 2 until you increase past the next power of 2, then allocate up past the next power of 2 for the memory that you need on the stack. Regardless, all of your variables are being pre-allocated by this instruction right here before you even enter any of your C code. So every variable that you declare in your code, all of the boxes are created on function call rather than on this on the line that they're declared. So if I say int I for int j and in K right here, and don't assign them anything, they are still all going to be allocated if I do something fancy like this and tell them to stop optimizing away my damn variables. If I say volatile, so this is actually the point of the volatile keyword. Volatile, I can't spell volatile, but yes, if I actually declare my variables as volatile, they're going to stop getting them to all disappear. So we can see here that they are actually all being pre-allocated by this subtraction from the stack pointer before we even have to assign anything to them. They're all pre-allocated with this subq command right here. Long story short, even though we could have a ton of code right here and it could be doing a ton of stuff, it's still all being pre-allocated. That's the gist of it. And that's actually going to be important later today when we talk about dynamic memory allocation rather than static memory allocation. So this is static memory allocation. We know how much memory we want to use beforehand because we are literally declaring all of these variables. But in the event that we don't, we have to dynamically allocate that memory. So let's go back to our very nice little pointer example in I equals 0. And we want to know where I lives. So to know where I lives, we ask where I lives with the where is your address operator, which is the ampersand operator, ampersand I. And then to store where a variable lives, we have to put it into a pointer variable. So int star I, and then pointer to I equals where I lives, effectively. So this is probably the most basic pointer demo. Now, this is where things start getting more fancy, because now that we know where I lives, we can do some very special things. Once we know where I lives, we can now directly write to where I lives. So the next thing we want to do is say, okay, I know where I lives, so I lives at x plus 1. We're putting x, or x minus 1, sure, we'll say x minus 1. So we know I lives at x minus 1, and we've stored this in some variable called pointer to I, right? Pointer to I. And this lives in a box that's somewhere on this same line, and it has its own address at some x plus y plus 1. And in theory, this is the size of the system bit width. So this is, if you're on a 32-bit system, pointers are 32 bits. If you're on a 64-bit system, all pointers are 64 bits. That's why I was able to print it as an unsigned long. But we're not going to bother worrying about that right now. So let's do a return 0. So we have our guy. He's living right here. But now let's say I know where I live, which I do know where I lives, but I want to actually change what's being stored inside of I with just the knowledge of where I lives. well, this is actually very easy. Because we know where I lives, there's no reason we can't say who lives at this address. Let's change what's being stored at this memory address. So we had discussed about L values yesterday, and so far we know about 2 different types of L values. So L values, remember, are where things live in memory. So the 2 types of L values we know so far are variable names. So these are things that can be used on the left-hand side of an equality operation, where we assign, or not an equality operation, but an assignment operation, right? So the first thing being variable names, because guess what? Variable names are literally just shorthand for a location in memory. So effectively, L values, or locator values, are actually referring to locations in memory, but pointers are literally the numbers at which these values live. So pointers can also be used as locator values. We just have to actually say, hey, I don't want to change what's inside of this box. I want to change what this box is referring to, which is this. And the way we do that is basically the inverse of the address operator. It's called the dereference operator. And it is a prefix star and then the name of the pointer. So pointer to I is now referring to I itself. So you can basically use pointer to I as a stand-in for I itself. So we're going to say, let's hang on. So if I do int j equals pointer to I right here, we're going to do this. And now I actually want to just print this out to demo this really quick. Printf, let's see, we're printing out a D and %D, and we're going to be referring to J right here. So this is the most basic demo we have here. It should print out 0 because we're storing 0 in here. Let's store 4 in here instead. Sure. So effectively, what we're doing in here, let's actually take a look at what's going on here, and this will be a lot of fun. I'm going to do out this entire program in MS Paint.land. Hang on, new, don't save. I'm going to take this and put him over in here. So first things first over here. What's going to happen? The first thing that's going to happen on, let's see, what error, if any, would be thrown for a double dereference on the I pointer? None. C does not worry itself about such trivial things. I can show you after we have gone through this example, Matt, what would happen. So this first line right here, in I equals 4, what does this do? Well, it does 2 things. It creates a box. The name of this box is I. This box lives at X, and it puts 4, the number 4, inside of this box. So the next thing that happens is this int pointer to I right here creates another box and then puts in where I lives. So it sees this reference to I operator, takes where I lives, which is this letter X, which is the memory location, and puts X into this box. And this box is named, I'll just call it PI, standing for pointer to I, instead of actually writing out pointer to I like I did last time. So now this int J creates another box right here for J, and we're calling this box J. And now what's going on with this statement right here, we do a pointer dereference on X. So what this is saying is, hey, who lives at X? What's being stored at X? Oh, I is being stored at X. Let's take the value that's inside of this and put this in our box right here. And the 4 gets put into J. And then we print out what's in J, and the result is 4. So this gets sent to printf, and we get 4 out. So effectively, we have this very fun little thing right here where J is being assigned at whatever's being stored in pointer to I through this pointer dereference right here, which is 4, and 4 is being then copied on this line over to J. So that's our initial application here. It's just this little silly program that copies something to another variable via a pointer. Obviously, you could do this instead by literally just having it say, set j equal to I, right? And because j is a location, it would create our j box and literally just copy what is in here into here. But this is an example of using a pointer, getting the address, storing the address, and then using a dereference to actually get what's in this first box. So does anyone have any questions about the address of or pointer dereference? This is like the most complicated thing. If you understand this, you basically understand all of C. So it's important that everyone understands what a pointer dereference is. This is like, you know, the big thing here. If you have any questions.
The part, what did we make X here again? I don't see in the code.
X is the memory location of I. So this is the actual location at which I is being stored at. So what's interesting is that these are actually literally all stored next to each other. So the end of X is X plus 4, but that's actually the address for the start of the pointer. And then the pointer is going to be of size 8. Almost always pointers are of size 8 because 64-bit systems. And then J is actually going to just be stored at X plus 12, the memory location.
Oh, so is that like what you were talking about before? You can do bit shifting if you wanted to do like, or like you want to do like some pointer magic, you could just add and subtract.
But don't, because pointer addition is something entirely different. And if you treat X plus 4, if you treat a pointer as an integer and then do +1, you're going to have a bad time because pointers have special semantics associated with them where the type actually determines the amount that's added. So if you do +1 to an integer pointer, it actually does +4 because the ints are 4y. And they were like, oh, this is a good idea. But if you're just trying to do +1, you could cast a pointer to an unsigned long and then do magic on that and then +1 to that to literally get like a chunk of an int that cuts into another int. But please don't. It's not good.
Nah, I get you. That's fun though.
Yeah, it is fun, but it's undefined behavior. You should never do anything like that. So again, this is a very basic, bare bones pointer example here, where we are literally declaring a box, getting where the box lives, putting it into a new box, and then using what's inside of our pointer box to find what's inside of our other box. So this basically says, hey, it lives at X. The pointer dereference here is the most complicated thing. I think everyone can really understand this step right here of saying, hey, where does I live? This spits out the number of where I lives, and then we put where I lives into this box right here. The more complicated thing is this step right here. The star pointer to I literally takes this X and returns the reference to this I right here is the confusing part. So what's interesting though is that a dereferenced pointer is an L value. So so you can also assign to this, and this is where things start getting really, really funky. So I'm going to do another example here. And instead of creating a new box called J, we are literally going to write to J write to I through the dereference pointer. So I'm going to write the number 6 to here and then print this out. So off the top of our heads here, we see that this program returns 6, even though we're printing out I. But I never set I to anything else directly. I'm literally writing to the memory location of I directly with a dereferenced pointer. So let's do this as an example using our box magic in MS Paint, because this is a fun one. So next one, new, don't save. Okay, so first things first, once again, we are going to be creating our box. Our box is named I, and we are putting the number 4 into our box, right? Then we're creating another box, and this box is our pointer to I, PI. And we are taking where I lives, which is at some arbitrary memory address X, and moving that X into pointer to I. That is this line right here, does both. It creates the box and puts where I lives into the box through the Ampersand operator. Now, this is the more confusing thing. Effectively, what we're saying is this expression right here, star PI, right here, evaluates to whatever is being stored at the address here. So what's being stored inside of PI is X, and then we're saying who lives at X? Oh, it's this block right here. It's this chunk of memory. And we know it's an integer because we declared it as an integer pointer. So it views this as a 4 wide chunk of memory. And now it is writing the number 6 into whatever this evaluates to. So it overwrites this 4 with a 6, and then when we print, it's actually outputting what's in I. It's literally looking at I and saying, oh, what's in I? Well, now it's a 6, even though we've overridden it through this dereference pointer. So now this outputs a 6. So effectively here we're using a pointer dereferenced pointer as an L value, and we're basically able to overwrite the value of this variable without ever actually touching the real name of the variable I, just by getting where I lives and then writing to what's actually being stored inside of I. Okay? So these are two of the straightforward. These pointer examples are not ideal for understanding what the application of pointers is, but it tells you a little bit about what pointers actually physically are. So if anyone has any questions about pointers right now, before we move on to pointer applications, feel free to ask. I see Dan Yee typing. I still have to talk about some other things here. I'm not going to do handles as strings tonight. Let's get rid of that. So address and dereference operators, good. Would the dereferenced value be 6? No, so effectively a dereferenced value is the same as a variable name. You can literally think of a dereferenced value as being a writable memory location. The same way when you say I equals 5 right here, you're writing 5 to the memory location that I is a named memory location, right? Now instead of a named memory location, it's a numbered memory location, and we're saying write to the memory location inside of pointer to I. But it's naming the same memory location as the letter I, effectively. And then did pointer to I, printf pointer to I, would it be 6? Yes, the same way if you did printf I, so if I did printf pointer to I, this is the dereferenced version of I. It literally is saying, hey, what's inside of this memory location? It's an int I. It's the same thing, right? So if we do dereference pointer to I, it's also 6 right here. Yeah, you're right, Dan. So also, if I didn't write the number 6 to this, we can get what's inside of I by doing a pointer dereference. So if I just create a pointer to I, and then I print out the dereferenced pointer, it's printing out what's inside of that address, which is 4 here. It's easier to think of variables as named memory locations when thinking of an implementation. Yeah, it's easy to think of variables as literally just being names for locations in memory, which is literally what they are behind the scenes in the assembly. Quite literally, if we take a brief look at the assembly code, I equals 4 right here is literally the location of offset from 12 from the bottom of the stack right here. So there is a 4-byte location on the stack, which every time you see them use the number I, or the variable I, they're not actually talking, they're not talking in terms of I, they're talking in terms of this memory address right here, which represents I. So yeah, you can think of pointers, not pointers, but variables, any variable name as a named memory location. And you can think of a pointer as a named address location. So you're storing where some other thing lives. And you can also have pointers to pointers where you start getting star, and then multiple dereferences. So let's do something fun here. We can do a double pointer. So I have a pointer to an integer pointer. So this is, I'll actually call this just PI to make things faster. So now we're going to have PPI equals ampersand to PI. And now we can double dereference to get the original thing, star PPI. And this is a whole lot of work. But effectively, here we're saying we have a pointer to a pointer, by the way, you read variable names backwards in C. This is a useful trick once you start getting more advanced stuff, especially when you start realizing that pointers can be constant. Like the pointer value itself can be constant. So you'll see things like const. You can have const volatile pointers as well. Const volatile pointer PPI. Like this is legal code. So this is a pointer to a volatile constant pointer to a constant integer. So you read variable names backwards in C once they start getting really complicated. That's how you understand what the variable actually is. So int star is a pointer to an integer, effectively. So let's actually, I feel like this would be a good demo to do out really quickly. Let's take a look at this. New, don't save. All right. So first things first, box with 4 stores the number 4, has the name I. Next up, create another box. This is PI. PI stores the location of, so I'm actually going to have these just be contiguous in memory like they would be on the stack. So this pointer's memory address is actually going to be at x plus 4 because this box is of size 4. And then this pointer starts at x plus 4 and then ends at x plus 12 because this box is going to be of size 8 because pointers are 64. For our purposes, if you're on a 64-bit computer, all of your pointers are going to be size 64 bits, so 8 bytes. So effectively, we're creating the second pointer and putting the address of I, which is x, inside of this box. And now, on this next line, we're creating another pointer, PPI, and we're storing x plus 4 here. So then, when we actually go to dereference PPI, so the first dereference here, PPI, evaluates to, so here's the thing. The dereference operator literally doesn't have to take a number. It doesn't have to take a literal pointer. It's just taking a memory location and giving you a way to write to that memory location. So PPI is literally equivalent to x plus 4. So what's inside of PPI is literally x plus 4. So then when we dereference x plus 4, which is this memory location, the first time, it's giving us a writable location to this chunk of memory right here, or writable or readable. In this case, if it's constant, if the pointer is constant, it's not readable, or not writable, my bad. But if it's constant, it is readable, but yeah, not writable. Okay, so first dereference gives us this memory location right here, and then this is spitting out, basically, our memory location for, so this actually spits out x, and then we're dereferencing x, and that is giving us this memory location right here, and it is going to just be printing out whatever's in this memory location, and it's 4. Easy peasy, right? So this is multi-pointers, so this is a double pointer right here. So that's fun. You can do a lot with pointers, but this isn't the primary pointer application. We're just scraping the surface of pointers right now. Any other questions about pointers before we continue? This is the basic pointer basics. I assume most of you already know pointers, so it's not actually that scary. I think there was, the person who didn't know pointers isn't here today, or didn't know C isn't here today, so I think most of us already get pointers. So now let's do pointers as handles to arrays, and this is the real place where you're actually going to use pointers all the time. So yesterday we were declaring arrays of fixed sizes. So when we declare an array of a fixed size, so I say int I, let's call it list of size 5 equals I, or not I, what am I doing? Size of, let's have it be a list of things and literally just have it have 1, 2, 3. So this is a fixed size list in C, and I'm not using the right notation. It is brackets in C. I'm thinking in Python still. Terrible. I was using Python earlier today, and now I'm doing everything in Python notation. Okay, So here we have a list of 3 things, 1, 2, 3, right? Pretty straightforward. So we were talking about lists yesterday, and basically how you can view lists as literally references to numbers, but that wasn't entirely truthful. If we actually do, let's actually print out what list itself is. Printf %u, and let's print out list itself. Now we should see something interesting, and they want a semicolon. Of course they do. And hang on, what's this? Do you see what this is? This looks awfully familiar. This looks like a memory location. And yes, it is. So lists, when we declare lists in C, list itself is literally a pointer. So when we declare an array, it's actually secretly declaring a pointer for us. So lists type is actually an int pointer. So I could say int pointer list p list is actually list itself. The list itself is a pointer here. And here I am literally just copying the location of an int pointer into an int pointer. And that's why this doesn't throw any issues, because this is literally a memory address of list of these 3 boxes. And this is a pointer to those 3 boxes. So let's actually take a look at what's going on when we use this list. So I'm going to copy this, and we're going to file, new, don't save. Let's take a look at what's going on here. So when we declare this list of integers right here, what we're actually doing is declaring 3 boxes with 4 each, right? So there's 3 boxes. Each of these boxes is of width 4. So this is at x, this is at x plus 4, this is at x plus 8, and there's these 3 boxes here. So effectively, what we're doing when we declare the list is saying, oh, this list references all 3 of these guys right here. So list is something that refers to all 3 of these. But what this list actually is the pointer to this location right here. So what we're actually doing is creating a box right here called list, and this is list, and list has x inside of it, which is the location of the first memory location of these 3 boxes. But these 3 boxes are contiguous in memory. You have x, x plus 4, and x plus 8. So now, when we actually access elements inside of our list, we're going to ignore this example where I copied this over because this is particularly interesting. It's just creating another box, and it's just taking whatever this is right here. This would be some memory location y, putting it in y, and this is called plist. Actually, no, it's plist and then copying x in. I'm not I don't know what I'm talking about here. This literally just puts in x to some other pointer, and we don't really care about that. That's not very interesting. What's more interesting is how we actually access elements with the access operator for arrays. So if we actually go back here and look at how we access memory locations, we use this operator right here, the subscript. There's subscript 0 gives us the first element, subscript 1 gives us the second element, and subscript 3 gives us or 2, my bad, not 3, gives us the third element. And then we can actually go over this and ask for the 4th element, but there is no 4th element, 5th element. And eventually, if we keep putting stuff in here, you're going to see that we start getting out random jargon when we're asking for the list. But this doesn't make that much sense until we start thinking about what this actually means. So we know that the list is 3 numbers stored contiguously in memory. But what we're actually asking for when we say list sub 1, it's actually, so list sub 1 is actually doing some kind of pointer dereference, because you probably remember from yesterday, I'm able to actually set values of the list using this, turning this into an L value. So if I say list sub 1 equals, let's put the number 6 here, and then I check what's in list sub 1, I'm actually editing that second box with this subscript right here. But what's actually going on here is we need some way of getting this. So there must be some way that this is being turned into a dereference pointer to a memory location that we can actually access when I do this. And the secret here is all that's happening is we're doing pointer arithmetic and pointer pointer arithmetic and a pointer dereference. So what's actually going on here, when I say list sub 1, it's equivalent to doing list, the value of the list pointer, plus whatever's inside of these brackets. So plus n, I'll have it would be plus 1, but I'll do plus n for some arbitrary, if you want to access an arbitrary list element, and then dereferencing this right here. So this is the real secret, that anytime you get a list element, what you're actually doing is adding that to the pointer to the list and then dereferencing it. So effectively, these are equivalent. So I'm getting the address of the second element and then dereferencing it. So list plus 1, this is pointer arithmetic. So instead of doing plus 1, it's looking at the size of this int list. So it sees that this is ints. It realizes that each int is 4 wide. And when I do a pointer plus its size, so list is a pointer to an array of integers right here. So it knows that these integers are 4 wide. And if I do list plus 1, it's not actually going to output x plus 1. It's going to output x plus 4 because it knows that ints are 4 wide. We do list plus 1. This returns x plus 4. And then when we dereference this, it literally gives us a handle to x plus 4 that we can now write to. And we can then write in whatever we want. In this case, we are writing in 6 to this memory location right here. And so that's actually how you do, it's actually what pointer indexing for arrays is behind the scene, which is very interesting. There's a lot of fun stuff here. And you can actually see this play out inside of this guy right here, where they're actually doing these allocations. This is actually pretty interesting, where we can see them doing all of this allocation right here. And yeah, so it's actually doing the subtraction right here. And then the pointer itself is going to be, let's see, where are they actually storing the pointer? Do they store the pointer here? List. So where are they actually allocating list? 1, 2, 3 into here. They actually might just be optimizing the list out of existence right now, which obviously the compiler is going to work all of its fun magic to optimize as much stuff out of existence as possible. If I print out the list itself, they're probably just going to return the RVP instead. Are they? Yeah, so they just literally return the first value instead of actually storing that in memory. They don't actually even have to store it in memory. It's just a virtual construct that they're optimizing out of existence here in the compiled code. So that's pretty interesting. But long story short, let's go back to our how's everyone on pointer arithmetic? Are we all set on that? We can then now move on to void pointers and probably, let's see, 9:21. I want this to end by 10. How do I best break this up? Probably like 20 minutes on, oh, do I want to cover structs tonight as well? That's pretty fast. I don't know. I guess I have to cover structs because of project 1. Okay, so let me try and do pass by reference in 10 minutes. Probably shouldn't be that bad. Any questions on pointer arithmetic before we move on? Pointer arithmetic, literally just when you do a pointer plus a number, instead of doing plus the real number, instead of becoming x plus 1, it becomes x plus the size of whatever this int is. So if you cast a pointer down to an unsigned long, it would actually, you'd be able to edit individual bytes. But since we don't do that, and we're adding chunks with the size of whatever the type of the pointer is, we're able to basically save ourselves a ton of hassle. But if you don't know that it's doing that, it can become quite scary. Okay, so why don't we take a look at pass by reference with pointers? So let's do the most classic example of a pointer application besides arrays, obviously, is the number 1 application, are swap. So the swap function is something that's going to swap the values of 2 variables. So you would not be able to do this with normal variables. So we're going to pass in an int A and int B. So let's say that we want to swap what's inside of A and B. So we have no idea what pass by value versus pass by reference means. We just want to create a function, which is going to be some black box that's going to swap the contents of what's inside of these 2 boxes, right? So let's do this. So I'm going to have some int a equals 5, int b equals 10, and I want to call this function swap, and I want to pass in a and b, and effectively I want this to, by the time this function is done executing, I want whatever's inside of a and I want whatever's inside of b to have switched with each other. Okay, so when I do printf, and I'm going to print out two numbers here, %d, I'm going to have a be here, and then I'm going to have b be here as well, %d. You can do this, and I know the people who are doing the homework know that you can do multiple things into printf using vargs. We'll be talking about vargs next week. The reason that printf is able to accept a seemingly infinite list of parameters. So we're going to printf a and b here. So effectively, we can see here that a is 5 and b is 10. Very nice, very straightforward. But we want this swap to actually do something to swap these two numbers. So the way that we might think to do swap might be something like how you would do a swap in Java, which I believe you actually have to use wrappers in Java because primitives in Java are passed by value rather than by reference. But in C, it's actually quite similar. Everything in C, though, is passed by value no matter what. So the question is then, how can we pass by reference? But let's just take a look at swap really quick. So one way to swap things is you have a temporary value, int temp tmp equals a. Then we're going to have a equal b, and then b equals tmp. And I don't know why I have this as an int. I want this to be a void. We're not returning anything. We just want to swap what's inside of the boxes. Now, the issue here is we see that this actually doesn't swap anything. But if we actually place this print statement inside of the function, we see that it actually does swap them. So inside of this function, we are swapping the values of what's inside of a and b. In this case, a now holds the value 10 and b holds the value 5. We started off with a is 5 and b is 10. And now a is 10 and b is 5. So yeah, clearly this algorithm works. We've swapped what's inside of the boxes, a and b. But the issue is the swap reverses itself, or appears to reverse itself, once we are back inside of our main function. It doesn't seem like this change is carried over. And that's exactly right, because these aren't the real a and b. These are copies of a and b that are made when we make the function call. And here's the big distinction between pass by value and pass by reference. Pass by value makes a copy of whatever you're passing in, copies it to a new memory location, where pass by reference uses the original memory location that you want, that you passed in. So effectively what's going on here is that when we pass in a and b, they get copied into new boxes. So let me actually do this out here. In our file, new, don't save. All right, so what's actually going on here? Right here, we create a box. This box is called A. We create another box here called B. A gets 5, B gets 10. Now we call this new function swap. So this was at some memory location X. This was at some memory location X plus 4. Now we call this new function, and we have now created a new A and a new B. And when we called this function, these parameters, when we called with these parameters, A and B, our parameters, had new memory locations created for them inside of the scope of this new function and had the 5 and 10 copied over. So now we have another variable here called temp, obviously. I'll call it t here for the sake of our sanity. First things first, we copy the value of a into t. Then we say that a is equal to b, so we shift 10 into here, rewrite this 5 as a 10, and then shift tmp, which is t, into b. This 10 gets crossed out and replaced with a 5. So as you can see here, we have swapped a and b, but we've swapped these copies of a and b. We haven't actually swapped a and b themselves up here. So when this function returns, all of these values get yeeted into oblivion, and that's it. And now all we have left are our original values, and when we try printing them out, yes, we get 5 and 10. So the issue is we don't want to make a copy. We want to edit these memory locations directly. So the way that we're actually going to do this is by passing pointers to these memory locations so they can actually be swapped. So now instead of taking in an int a and int b, we're going to take in a pointer to a and a pointer to some b. and we're going to have temp be a pointer. So effectively what we're going to be doing is, instead of rewriting the actual locations, we're going to swap we're not actually going to swap the addresses, we're actually going to swap the content. So our temp is now going to be whatever is dereferenced by A, and now when we write to A and B, we're actually writing to the dereferenced values of A and B, because A and B are now pointers. So this, let's see, so we're doing a dereference to B as well, and I believe this should work. They're going to get mad at me for something, though. I'm almost sure of it. Let's see, what are they mad at me about right now? Passing argument swap makes a pointer from an integer without a cast. Oh, yes, because now that we're passing pointers, we have to pass in where A and B live. We're not passing in A and B themselves. And huzzah, this actually does the swap. See, we've done A has been swapped to 10 and B has been swapped to 5 out here in main. So let's actually go through how this works in physical space, or in hardware land. So let's do one of our fun little demos here. So I'm not going to save this. Okay, we're going to make that scrunchy, and let's draw it out. So first things first, we create the box A and we create the box B. So here's the box A, here's the box B, here's A, here is B. A lives at X, B lives at X plus 5, or not 5, plus 4, because integers are 4 bytes, not bits. Now we're getting where A lives and we're getting where B lives. We're putting them into parameters. So you can think of parameters in terms of being stored in memory as literal locations. So here is our A pointer here. So now A is actually a pointer in the scope of this new swap function. So this is actually an entirely different place in the stack, SWAP, and this is main up here. So this is the scope of main. So now we have B over here, and B is a pointer as well. And we're actually putting where A and B lives into these. So now A is going to be X and B is going to be X plus 4. So now we're also creating another variable called TMP. And TMP is, I'm just going to call it T. And what are we putting into TMP? Well, we're putting whatever lives in A. Oh, I forgot to put that 5 lives in A and 10 lives in B. Easy peasy. So first things first, we dereference A. And when we dereference what's in A, and that's referring to this A, we get this memory location right here. And because we're then reading that memory location, it reads 5 into T right here. Now, this next step, we do the dereference location. So the location of A equals whatever's being stored inside of B. So A now is being set to whatever is inside of B. So A, the contents of A, gets crossed out and has the contents of B move in here. So that's 10. And now the contents of B equals whatever's stored in temp. So then this 10 gets overridden with A5. So you can see that this function right here, our swap function right here, is actually operating on memory locations in our main function. So that's what be passed by reference does, is despite the fact that these memory locations up here are all inside of main, we're able to actually edit them because we have the context of what's inside of them down here in our swap function using pointers to them. So what's actually going on here, I probably should have written this out better. So with the actual statements of all of these referring to all of these different memory locations, but you should be able to get the general idea from this. And swap is the traditional example of why you need pointers for things. So pointers are useful in more respects than just that. For example, if you want multiple return values from a function in C, this is one of the things that you don't get out of the box. You have one return value, right? You can return an int, you can return a float. Normally, the way that you do multiple return values in C is you pass in pointers to things that you want returned. So you would actually have, so Microsoft actually has like special macros for all of this. But so say you wanted to add A and B and then get out 2 numbers as well. So say you wanted to have something that, let's call it add sub. So this function is going to return what the sum of 2 numbers is in A and B and what the subtraction is. So let's do int pointer sum and int pointer diff. So we're returning the sum of A and B and the difference of A and B. So the way that we're going to do this is we're going to do the dereference location of sum equals A plus B, and the dereference location of diff equals A minus B. So now we're basically able to get two results out of this function by writing to memory locations that were passed in from when the function was called. So in here, say I want to now have in sum of A and B and in diff of A and B. All I have to do now is call add sub with A and B and pass in the memory locations we want written to. So sum and diff. Very fancy, right? Or I guess it's, yeah, I do two diffs here, but this is wrong because that should be diff. And now I can print out the sum and the diff of the two numbers. Sum and diff, and then do sum and diff. Right, so the sum of 5 and 10 is 15, and 5 minus 10 is -5, right? So here's a function that has two outputs, and we're using parameters to collect our outputs. So this is typically how you do a function with multiple return values. You make it void. Sometimes in bigger, fancier libraries, you'll actually have, instead of it returning void, you'll have it return an error code. And then you can actually check from the output value whether or not the function failed or not. That's very common in C libraries. So I'm working with Vulkan a lot, and you see almost every Vulkan function returns some error code as like an int, and you can check whether or not it succeeded or failed by the error code, and then the actual output of the function, some object or struct you want to work with, is all done through output. You pass in the address of something that you want it to write to. Okay. So that is pass by reference. Let's see what's next on the docket. Oh, multiple return values with pass by reference. Good, we did that. All right, we're going to skip function pointers because you don't need them for what we're going to do for the project. We can do function pointers next week. I don't know if they're even going to ask about them because function pointers are kind of like considered the end game of C. Like once you have function pointers down pat, you're completely good. But we will ignore function pointers for now. Okay, dynamic memory allocation. So this is where things start getting important because so far everything we've done, do pointers / dynamic memory allocation, use non-stack memory. That's actually exactly what we're about to get into. So every example we've done so far has been inside of stack memory. So you heard me say here that we're in basically the frame of main. So main has some memory on the stack, and it's pre-allocated locations for everything in it. So A and B have been pre-allocated inside of main's memory. And swap here has two parameters and this TMP here, so it's pre-allocated 3 spaces for itself. But this isn't always going to be the case. There are lots of cases where you could say want some variable amount of memory for use in your own whatever the heck you want to do. So a good example of when you might need some variable amount of memory is, let's say you have a user who wants to input something, some big list of things. You almost always allocate dynamic memory in the context of lists. You allocate huge chunks of dynamic memory, and you can have stuff put in there. So a good example of when you might use dynamic memory is if you're ever asking the user to allocate something. So let's say that I want an array of 100 integers. Not 100 integers. Let's say I want my user to tell me how many integers they want. Something like that. So my user says, hey, James, I'd like a variable amount of integers in my program. I'd like, a list of 10 things, 20 things. I want to input what that number is myself. So there's 2 ways of doing this. As the programmer, I either dynamically allocate the array of what they want as some gigantic number, int f, or let's call it array. So they want 100 data points or something, or they want some variable number of data points. And I say, all right, you can have a variable number of data points. Sure, go for it. You'll never run out of space if I just allocate a gazillion things. But just you wait. I can actually do something like this where I actually have a RAM chart on my memory usage right here on Process Explorer. So you can see that my Potato PC right now has 8 gigs of memory. I'm using 5.4 gigs of physical memory right here. If I actually go type up a C program, which I probably shouldn't do, but because it will take an extra like 2 minutes, but what the hell, let's do it anyway. New window. Oh god, this is slow. This is very slow. New file. Select a language to get started. Oh god, this is gonna take forever, isn't it? Can I just like cat it? You know what? We won't do this. It'll take too long because I want to get things moving. But effectively, there's 2 approaches to this. So either I say, all right, you want to allocate a data point? Yeah, you can allocate as much data as you want. You can write to whatever you want because I've allocated you a gazillion data points and you'll never run out of space in this array. In fact, an interesting side note here is that in the automotive industry, you are not allowed to use any dynamic memory allocation whatsoever. You are only allowed to allocate static amounts of arrays because they consider dynamic memory allocation too risky. Because if you screw up that dynamic memory allocation, you're crashing someone's car, and that is not good. So in the auto industry, where they program everything in C with all of their embedded systems, you are not allowed to use dynamic memory. You have to allocate some big buffer ahead of time, even if you don't know what you want allocated in advance. So this is approach 1, but this uses like 10 gigs of RAM, and we don't want 10 gigs of RAM. So instead, we use something called the heap. So effectively, let's take a look at C program memory layout. C program memory layout. So effectively, you have 2 options for using memory. You either, oh, it's perfect, right here. You have all of your function calls and everything allocating memory on the stack. So every time I call into a new function that I'm using, so say I call, you know what, actually, let's take a look at the homework. This is a perfect example. So on the homework here, binary search, right? I don't know whose binary search this is. Is this mine? This is mine. Let's not look at mine. Let's look at someone else's. Who do I still have up? I think this is Dan Yee's. Let's do Dan Yee's binary search, but like his good one, not his, or not the, yeah. Let's do this one. Okay, so right here, if we take a look at Dan Yee's binary search, there's 3 different things here. There's a list of 10 integers, there's an element, there's a low, there's a high, and there's a midpoint. So effectively, what's being passed in here is so this is actually a pointer behind the scenes, but we're not gonna worry about this. They might actually be doing this copy. I have to look at the copy semantics for this, but long story short, what's being allocated on the stack is, so that's 4 plus 4, 8, 12, 16, and then let's just assume that's 8 and say 24, sure. So this is effectively allocating 24 bytes on the stack when this function is called. So when the function gets called, whenever Dan Yee calls binary search, we're creating 24 bytes worth of boxes in the stack space, okay? But let's say we don't know how much we want to allocate when we're making the call. Say we want the user to input something in that function. Then we have the option to allocate dynamic memory from the heap. So the heap is a special region of memory where we can ask the operating system to give us more memory on the fly. We can say, hey, operating system, give me this much memory. You might not know how much memory that is when the function is being called. And in that event, then you have no other choice but then to use the heap. So effectively, the stack and the heap grow into each other, and eventually the stack is going to hit the heap. And when the stack hits the heap or the heap hits the stack, you get what's called a stack overflow. That's the name of the website, because eventually, if you keep calling functions, you're going to allocate more and more memory on the stack until it crashes into memory that's been allocated for the heap. And then, kablat, your program is, you're rewriting over memory that you probably need, and that's problematic. And that causes a stack overflow. So let's look at, what example did I want to do? Let's see. I wanted to do an example of dynamic memory allocation for an array. So we're going to have our example. User wants to input the fact that they have some, excuse me, user has some amount of data they want to store, so that's going to be a scanf. And now we can actually explain what scanf is doing, because now we actually understand outputs from into memory locations. So int size of array equals, and we're not even going to assign it anything, and then we're going to scanf, so this is going to be user input. We're going to read we want this to be an unsigned, we actually want this to be unsigned, because you can never have a negative size of an array, so I'm just going to write unsigned here. Unsigned is not how you spell signed. S-I-G-S-I-N-G, how do you spell signed? S-I-G-N, unsigned. Oh, I'm missing the N. There we go. Unsigned int size of array. So we're going to let the user tell us how big they want their array, and we're only going to allocate exactly how much space they want. So I'm going to have the user tell us what number they want allocated, and we're going to give them an array that contains the numbers 1 to however big their array is. So effectively, if the user requests an array of size 5, we're going to give them the numbers 1 through 5. But otherwise, we'd have to allocate 5 spaces or a gazillion spaces off the bat every time this function was called, and that's completely unnecessary when we could allocate exactly how much memory we need. So we have the size, we're reading the size from the user. In fact, I'm missing here the ampersand, and now we actually know what this ampersand on scanf means. This literally means we are saying, hey, where does size of array live? And we're passing where size of array lives because we want to write to size of array inside of scanf. So scanf is effectively saying, hey, I'm going to read whatever unsigned integer you give to me on the input stream, and then write the result to size of array. So this is actually an example of an output function where you pass a pointer to the function, and it's then writing to that memory location. Okay, so now let's actually allocate the size for the array. So the first thing we actually have to do is hashtag include stdlib.h. So this stands for standard library, and the function for dynamically allocating memory on the heap is inside of stdlib.h. So let's actually get to allocating. We want to allocate a large array of memory. So since it's an array, we're going to have it be not a literal array. So we're not going to declare it as int array brackets, because this is talking about an array of fixed size of some amount. We're literally just going to have it be a pointer. So I'm going to say int star array, and this is going to be a pointer to the first element of the array. And the size of the array is the size that we want. And the way that we're going to do this now is we're going to use malloc. So malloc is the function that actually does the dynamic allocation for us. So what we pass into malloc is the size of the amount of memory we want to allocate. So because we want to allocate an array of integers of size of array, malloc only takes in the number of bytes that we want to allocate. So the number of bytes that we want to allocate is actually the size of an int, times the size of the array. So then multiply that by the size of the array. And now we have, what are they yelling at me for? Error, conflicting types, blah, blah. Oh, because I'm declaring this down here. Cringe, okay. So effectively, our guy malloc here is returning a pointer to a large chunk of memory that we have just allocated. So some people like to cast malloc to the type that's being returned from malloc. So malloc is technically returning a void pointer. It does not care what the type of memory it is, and then it's auto casting to an int pointer. But some people like to be explicit and say that malloc returns whatever type that they're casting to. So here I'm casting to an int pointer. So effectively, what malloc actually does is we are telling the operating system, hey, so you know what, let's actually do an example of this. Let me fill up this array with something. Okay, so let's actually then do for int I equals 0, while I is less than the size. We actually have the size of the array because we dynamically allocated it ourselves. I plus plus, and then we are literally just going to put in the index what it is. So I equals I. So now we are creating this big chunky array, and we're just putting in each index what the index's index is, right? So 0 contains 0, index 1 contains 1. But we're dynamically allocating this. We're giving the user full control of how big this array is, and we don't need to know what the size of this array is at compile time. The user, so this is the big distinction. If you need to know the size of something at runtime rather than compile time, if you can't know the size of something at compile time, it has to be dynamically allocated. If you do not know how big your thing is going to get because of user input, etc., you have to allocate it on the heap. It has to be dynamically allocated. If you do know how big it can be at compile time, you can statically allocate it by saying, okay, I'm just going to have my array be of size 100. And that's actually better. It's always better to statically allocate when possible, but you should, in the event that you do not know how big your array is going to be, you have to dynamically allocate it. Languages like C and C++, not C, but C++ and Java, array list behind the scenes is doing a ton of dynamic allocation. And in C++, vector does a ton of dynamic allocation behind the scenes. It manages your dynamic allocation for you. In fact, that's what the first project that I'm assigning is. So if we actually take a look at the homework for this 4-day vacation that we're going to have is actually going to be to create your own array list in C using functions. So you're going to be passing in, you're going to have some struct that's going to contain the size of the array list and the actual pointer to the dynamically allocated memory. And then you're going to create a bunch of functions that operate on an array list object when it's passed in. So I actually still have to cover structs. What else do I have to cover? I have 10 minutes to cover stuff. I'm hoping I don't go over. Let's see, Malloc. All right, I have to go over calloc, realloc, and free. Okay, once you understand Malloc, though, calloc and realloc are really easy to understand. And then I'll spend like 5 minutes on structs because structs are pretty easy comparatively. So let's take a look at our example here. So I really quickly want to go over what our example is actually doing in memory space. So let's not save this, and let's make this a bit smaller. So effectively, first things first, we're creating a location in memory inside of the scope of main. And this guy is called size of array. So this is, I'm going to call it S here really quick. So we're creating this box right here called size of array. We're not putting anything in size of array. We know that size of array lives at something X right here, okay? So next thing, we're actually going to scanf into size of array. And then scanf creates its own call stack somewhere over here. And then it's getting the user input and then creating this, it's actually getting the size and then writing that to this location using a pointer dereference. So let's say that the user actually inputs 5. So by the end of scanf, once it's done executing, it's written 5 into this memory location right here where size of array is being stored, okay? So the next thing that's going to happen is we have a pointer to some array here. So this is literally array. This is being stored at x plus 4 on the stack. And effectively, we need to compute what the address at which this is being stored is. And that's what we're handing over to the operating system. That's what Malloc does. So what Malloc is actually doing is it says, okay, operating system, I need this much memory. And my stack doesn't allow, I don't know how much memory I need at compile time, but I'm asking you to go find me this memory somewhere in, well, it's going to be in the heap. The operating system has set up your heap somewhere. So when I malloc, the operating system says, okay, I'm going to give you this memory over here in the middle of nowhere on heap. This is going to be heap. So the heap is over here, and the stack is over here. This is stack space, this is heap space. So the operating system is like, all right, what, you asked for 5 bytes. You're saying malloc 5. Okay, so I'm going to give you 5 times size of int. So I'm going to give you, hang on, did I just hit the camera? I think I just hit the camera. My bad. Effectively, so we've asked for 5 spots right here. So it's going to, it doesn't actually know that this is an int pointer. It doesn't know anything about the type of what's being passed in. We're just passing in a number of bytes. So the operating system in the heap says, okay, you want 4 times 5 bytes. So I'm going to allocate this big chunk of 20 bytes. So it's like a big box, 4 times 20. So this is a giant box. Doesn't have a name, but it does have a location. I'm going to call this location Y in the heap. Okay? So then it says, okay, congratulations, you have this. I'm going to pass this back into you. Here's your Y. But now, here's the interesting thing. Because we know that this array is of type int pointer, we know for a fact that we're looking at this from a lens of integers. So we are actually splitting this up into boxes. Not the operating system isn't doing the splitting. There's no splitting involved. We just are interpreting this as 4 wide integers, 5 4-wide integers on each of these. So this is y plus 4, that's y plus 8, that's y plus 12, y plus 16, etc., right? So y is being stored here, and when we interpret things and look at what's inside of there using, obviously, the subscript operator here, we're actually splitting it up, not semantically, but syntactically. So it's effectively, effectively, the program doesn't have any idea that these are ints. The operating system has no idea what's being stored in this memory. We're just looking at it from that lens in stack space in our program right here. But as far as the operating system is concerned, this is just some big chunk of memory, okay? So we've allocated this chunk of memory. We've put some stuff into this chunk of memory. Now we can work over in this chunk of memory with the reference that we have into array here. And so let's say then we want to print out what's stored in here. So if I do for, so what's actually going on here in this loop here is we're going through the size of the array and literally writing boxes, right? So we're writing 0 into the first box, 1, 2, 3, and 4 into the final box, which has been allocated over here, right? So pretty straightforward in that regard. The only other thing that we need to discuss is now, let's actually print this out. Sure, why not? Just show that this is possible. You can now read from here. For the fun of it, instead of doing the subscript, we'll do it with a dereference. So I will dereference the location. So we'll do a printf. Let's see, %d, since we're working with integers. And we'll do array +1. And this should print out however many things we're returning. But obviously, we have to put in what we want to scanf with. So we'll put in 5. And we should see it print out. Oh, they actually don't like this. What don't they like? What don't you like right now? Oh, because it's +I, right? It's not +1. Okay, 1, 2, 3, 4. Easy peasy. So the next thing that we want to talk about is, now that we've dynamically allocated all of this memory, the issue is that the operating system isn't smart enough to know when we don't want this anymore. So the operating system will leave this memory in existence forever, and this will be here like permanently unless we delete this. So anytime you call malloc, you have to call free on that pointer to let the operating system know that you're done with it. So free array. So this free function basically tells the operating system, hey, remember when you gave me that pointer to that thing? Well, I'm done with it now, and you can use that for another program. And then the operating system says, great, thank you, we're going to get rid of this. And now you no longer own this. And if you try and write to memory after you freed, even because you still have this pointer, you can still say a equals 3, you can still write to this. So I could say like a3 equals 5. It's completely legal to write to this, but it's not array 3 equals 5. It's still legal to write to this memory location, but this is undefined behavior because you no longer own this memory location. The operating system has said, oh, you've told the operating system, I'm not using this anymore, whatever. and now you still trying to use it is undefined behavior. So do not attempt to use a pointer as a reference after you've already freed the pointer. Anyway, so that's dynamic memory allocation. There's two other dynamic memory allocation functions that we should care about. The first one is going to be calloc, and then there's realloc. So let's actually, instead of me actually showing you them, we're going to look at documentation for them. Calloc, give me calloc on CPP reference. Please don't have this be really complicated. Okay, good. So calloc is actually pretty straightforward. So normally with malloc, when you do malloc, you actually have to do the multiplication by the size of the thing yourself. So here I'm doing malloc size of int times size of array. With calloc, you actually pass in the number of things you want as the first parameter, and then the size of what you're allocating as the second parameter. So it does the multiplication for you itself. So if I do calloc here, it does this. What's different about this is calloc, what makes calloc so special, is calloc will automatically write zeros to every single memory location. It will zero out every single bit inside of the allocated space, whereas malloc doesn't zero every bit. So calloc is actually slower because it has to modify every single memory location, every single bit in there. Whereas malloc doesn't, and you could have random garbage in there when you run malloc from what it was before it was given to your program. But calloc does zeros everything out first. So depending on your application, that can be useful if you have to have a zeroed out array of something. But typically you're calling malloc instead of calloc. So then the final thing is realloc, and realloc it's just what it sounds like. Reallocates a chunk of memory in the heap. So if we take a look at realloc here, you pass a pointer and then you pass a new size to it. So effectively, realloc is, hang on, I can't believe I lost realloc. Wait, what am I doing? Okay, so realloc, you pass a pointer that the operator has given you, and then you pass the new size. So let's say here in our terrible example that we've given, I pass in 5, and then let's say that later on the user is like, hey, that's not enough memory. I actually want my array to be bigger. But you've already written all of these values to the first 4, but now you want to extend your array. Or think of, we have Kyle in here. Kyle in here? Kyle's not actually in here. He's just complaining in chat. I was like, okay, Kyle, you're gonna tell me about dynamic memory. Thanks, Kyle. But effectively, think of an array list in Java, right? So when you have an array list in Java, you start off with no elements in the array list. Then you do add, and then it puts one element in the array list, another element. There's no way it knows what the size of your array list is at compile time in most cases. So every time it adds a new element into your array list, it has to modify the size of that dynamically allocated block of memory. And the way that you do that is with realloc. You literally give it what your pointer is, and you say, hey, reallocate this and make it some bigger size. So what you're saying is make it the size +1. And this is actually going to be a major component of your first project here that I've laid out, is in the add function, where you're passing in an array list and an element to add, you have to modify that pointer of dynamically allocated array. You have to grow it by one element. In real life, you're not just growing by one element. Array lists are super optimized, so they're actually growing by, they're doing the exact same thing the compiler does when it allocates stack space. They're growing by a power of 2, but we're not gonna do that. You're just gonna literally, every time someone says that they want to add something to their array list, you're gonna realloc your entire current array to be of size +1, and then you have access to additional space at the end. This can be kind of confusing. If you have any questions about realloc, call me, DM me. I'm happy to answer questions about realloc. All right, and then finally, we're going to talk about structs, which I really don't have enough time to talk about structs because we're already 2 minutes over, but I'll give like a 5-minute struct overview really quickly. Structs are very, very easy, okay, in the C programming language. All right, watch this. Struct keyword All right. And then we're going to give our struct some name. We're going to call it, let's see, what should I do a struct of? Let's have our struct be person. All right, so what is a, well, we don't know strings yet, so that's a terrible example. Let's have our struct be a circle struct. SIR, or maybe a rectangle. I think rectangle is better. Rectangle. So we have struct rectangle, and then our rectangle is going to have an int width and an int height. Okay, very straightforward struct width, height, easy peasy. Now we're going to say we want to create a rectangle in our rectangle struct. You have to write the struct keyword rectangle. This is a object. We'll call it an object. It's very similar to Java objects, right? These are your excuse me. These are your properties, and there are no methods. It's just properties. Every time you want to do a method, you have to pass the struct in as part of the method. So normally, as we're going to be seeing in our example here, you're going to have a struct which represents your array list. Your properties are the size and a pointer to the dynamically allocated memory. And then all of your methods are actually just going to be functions that take in a pointer to the struct. And effectively, because you're going to be editing what's inside of the struct, you have to pass a pointer to that struct. Okay, hang on. Back to my terrible struct example with a rectangle. So we're going to declare a rectangle, boring struct rectangle, and we're going to give it a name. Let's give it the name rect1. So here we've dynamically, this isn't dynamically, this year we've statically allocated a rectangle object. So all this has actually done is created a width and a height, some internal width and height, and it's been stored statically on the stack. So now we can actually write to this rect1 dot width. So we can access this internal member right here by doing the dot operator, very similar again to Java public members. And we're going to say that this equals 10 and rect1 dot height equals 20. So now let's say I want to create something that gets the rectangle. So I do int area. Area is going to take a struct rectangle parameter. And then we're going to call this rect. And to compute the area, who knows how to compute the area? It's very simple. You return the width. I don't know why I typed rect. Return rect width times rect height. And now if we just do return here, we should see, I'm going to return the area of rect1, and we should be expecting of course, because I named this rect1. All right, let's name this rect instead of rect1. Let's keep the parameter name consistent. All right, and as we can see, 10 times 20, 200, easy peasy, this outputs the area. Now let's say we want to actually edit what's inside of the rectangle, so something like a setter would be a void function, and we're going to be, since we're setting some internal thing, it's no longer enough to pass in set area. It's no longer enough to just pass in a copy of the rectangle. Keep in mind that this is making a copy of every single property in here, and then doing that, and then doing the computation. Since we want to pass in the actual memory location, we're pointer to a rectangle to set the area. Now here's where things get interesting, and here's a new operator for everyone, the arrow operator. So the arrow operator is what you use to access a property of a pointer to a struct. So rect arrow width is the same as, so rect arrow width. So I'm going to say rect arrow width equals, what am I going to do? So this is set, oh, I don't want to set area. I want to set width. Let's do set width, sure. So rect width equals, and then we're going to be passing in a new value. Call it width, sure. Rect width is equivalent to width. So this is actually shorthand for dereferencing rect and then doing the dot operator for width. So the arrow operator is literally just a shorthand for dereference object dot. So you almost are always going to use the arrow operator instead because it's just so much easier than using dereference and then dot. Yeah. So they're mad at me because that's... What are they mad about? Rect is a pointer. Did you mean to use... No, I did not, because I deallocated first. I guess that they don't like my order of operations. There we go. Okay. So yeah, it's shorthand for dereference, then dot. Okay. So here, if we do rect1, if we run set width and then reference to rect1, and then let's set the width to like 20. So now we're doing 20 times 20, and we should get... Am I crazy? Am I crazy? 144. It's 20 times 20 is not 144. I know for a fact that 20 times 20 is not 144. What have I done wrong? No way I changed this and this goes back and this becomes the right answer. No, 144. Right. Okay. Why though? Because area is clearly doing width times height. Set width. Oh, wait. No. No. Reference to rect1. What have I done wrong here? Clearly something is wrong here. 20 times 20 is not 144, right? Right? 114, area of rect1. Rect1 is being edited by this function right here. This is clearly editing because I'm dereferencing the object. Oh, no, it's because I'm dereferencing the object doing dot width. What I actually want to do here, dereference the object, and then write to the width location of the object. So what I'm actually wanted to do was rect.width, and then, no, but rect is a pointer. Even if I undo this entirely, this is still 144. No, now it's 200, but that's expected because that's 10 times 20. Even when I try writing to this memory location, it doesn't let me. It doesn't like this. Why isn't it like this? This should be completely legal. This is exactly how you do it. Rect is a pointer. I'm accessing the location. I'm writing width to it. Width is 20. And now we should be doing width times height. What have I done here? Set width calls this. Do I step through this or do I spam printf? I'm spamming printf. Printf.
Wait, do you have to use the arrow for in main for rect1.width and rect1. No, because that's just a struct, it's not a pointer.
No.
No,
Yeah,
okay,
exactly. Exactly. So it's actually being stored in stack memory here, which is why I can use the dot. Because we literally have that direct access to it. Whereas in here, when we're calling in a separate function, we need the pointer to it because it's being stored in the stack memory of a separate function.
Yeah, so you're sending through the pointer to set and then you're editing it for that new width. So you do could it be because so you're computing the area with rect1?
Because this should be setting the actual internal thing of rect1 because this is a pointer and we are editing the width from here.
Can you try printing out what width is when you calculate area? Just add that into and see maybe if it's not getting edited at all.
Printf %d. Hang on. %d rect.width. So it is making a copy, obviously. Yeah, it says that the width is 20. What?
Yeah.
What does it say the height is?
Yeah, I guess that would be the better question at this point.
Oh, I know what's wrong. I'm 99% sure that the issue here is the fact that it's only... All right, so what if I printf %d area? Because I'm pretty sure we're returning like an unsigned int or something. So it like maybe an unsigned char. So I actually don't know what the program is allowed to return. There we go. Okay, the issue was just the return statement. I'm sitting here like, what's going on? How is this happening? And the issue was just that the return, because return is like truncating it, it doesn't recognize it as like, it's some weird error. So they're like, okay, we're just going to return 144. But here we're printing out, yeah, so 8. I don't know what they mean by program. Oh yeah, program return 8. There we go. Okay.
Why would it have a problem return? Well, I guess you were returning from a void. Okay, you were returning something that was void.
I was not. I was returning area. So if I put area here, it's the same computation, but it says 144. My guess is that there's some weird thing where they're like truncating this and they're like, you can't return that code, or the return code means the same thing. So they truncate it to a different return code. So it's like, you know, so don't use this faithfully for outputting integers from main as your program returns.
Yeah, I guess.
Always print it out. Never trust it. Anyway, if anyone has any questions about assignment 1, I'm all ears. This is probably one of like the most powerful things that you can do, is to write your own data structure. This is going to be we're basically writing the data structure for an array list from scratch. So an array list in Java, as you may know, has these methods you can call, add, you can set things in it, you can get elements from it, and you can get the size of it. So C doesn't have anything built in like that. C++ does, it's called vector. But effectively, any Python arrays are basically array lists by default. They have a I think it's a .add method that lets you basically do the exact same thing. And it's good to understand how these things actually work under the hood, with realloc and malloc, because under the hood, almost all of this is written in C. Everyone's stuff is written in C. So if we actually take a look at what I'm expecting to have done, I'm basically expecting you to write an array list class, but it's not a class in C. You're just going to be working with a struct. It's going to be an array list. I just want it to be an array list of ints. So you're going to have an int pointer that's going to be your dynamically allocated memory. And this is actually where all of your integers are going to be stored. This is your actual array. And then you're going to have a size element stored in here as well. So then you're going to be creating an array list. And you're not actually going to be setting these yourself in this function. You're going to be calling methods. And when I say methods, I mean like meme methods. You're going to have a void create array list that's going to be taking a reference to an array list, or a pointer to an array list. Struct array list pointer a. And in here, you're actually going to be doing your malloc, where you say array list, dynamically allocated memory. Oh, I guess you're going to pass your size in here as well. Int size. And long story short, you're going to then just say you're going to do your malloc right here. You're going to dynamically allocate it, set the size. And then in all of your other methods, you're going to basically twiddling around what's inside of the dynamically allocated memory and the size based on adding new things. I guess you could write, I didn't write them for move thing. You can write a remove thing if you want, where then you have to shrink the array and remove an index from it. That's a fun one to write, but I didn't put that in here. And then in the bonus problem, I have a linked list, and linked lists are also really fun to implement in C with structs. You have a linked list node that points to itself. Anyway, I'm already 17 minutes over time, so thank you for coming tonight, everyone. It's been fun, but we will wrap up here. If you have any questions this weekend about how to do any of this, by all means contact me. Also, since we didn't go over strings, we can get rid of bonus problem 1. Don't bother doing the array list of strings. Just worry then about a list of ints as well. That would be a fun one. So a linked list will be the bonus problem. And then the main problem is going to be making the array list data structure. And if you're feeling extraordinarily ambitious, we'll have bonus problem 2, write a binary tree in C. and give me like the standard binary tree functions. Binary tree in C, and then give me like a binary breadth first search, depth first search. Binary tree in C with breadth first and depth first search. I don't even think I'll implement that, but like if you're dying this weekend and you're really bored, feel free to write a binary tree and see. That's a great exercise, and I'll look it over for you. Okay, so with that, I would say we're done here. I know Dan wants to stay after to discuss some IEEE server stuff.